Good morning, everybody. Today we will continue with the first law of thermodynamics. This lecture will also be a brief lecture. I will not go into detail. For the details, you can visit the course book. We will learn how to calculate work done by a system when its volume changes. Okay, and then we will learn how to interpret and use the first law of thermodynamics. And we will talk about 4 important kinds of thermodynamic processes. And we will also discuss why the internal energy of an ideal gas depends on temperature only. This is the change in the internal energy of an ideal gas, delta U. So we will talk about this. Actually, this lecture is about this delta U, okay? We will mainly talk about delta U. Delta U, the change in the internal energy of a system, is given with this expression, Q minus W. This Q is the heat added to the system. We have a thermodynamic system, and we add heat Q to this thermodynamic system, and this is the work done by the system. Okay, so this is the summary of this lecture. This is the first law of thermodynamics. The change in the energy of the system is given with Q minus W. So we will talk about this equation during this lecture, and we will discuss different situations. And we will also learn the difference between molar heat capacities at constant volume and constant pressure. So during the last lecture, we have learned molar heat capacity of gases and solids. And today we will discuss the molar heat capacity at constant volume, CV. And we will also discuss the molar heat capacity at constant pressure, CP. Okay. And finally, we will analyze adiabatic processes in an ideal gas, and then we will finish this chapter. Here you see a steam locomotive. Of course, they are not in use today, but in the past they are widely used. And this type of locomotives operate using the laws of thermodynamics. Also, the air conditioners and car engines use the laws of thermodynamics. Okay, and during this lecture, as I told you, we will talk about the energy. We will talk about the internal energy of the system. We will talk about the conservation of energy in the form of the first law of thermodynamics. So this lecture will be about this equation, Q minus W. This is the internal energy, the change in the internal energy of the system. Let's consider that the steam locomotive has an engine, okay? And you add heat to this system, and then this system does work, okay? Then this gives us the change in the internal energy of the system. So this is the first law of thermodynamics, and today we will discuss this one. So let me discuss the thermodynamic system. What is a thermodynamic system? A thermodynamic system is any collection of objects that may exchange energy with its surroundings. Here we have a pot, let's say, okay, and here we have a heat source, and we have popcorn within this pot, okay, and this heat is transferred to the pot, and then this pot transfers this energy to the popcorn. And then what happens? Popcorn applies a force on this lid here, okay, and then moves the lid. So then popcorn does work, okay. We add heat to the system, and then system does work, okay. So then this is the change in the internal energy of the system. This is the heat given to the system minus the work done by the system. Okay, so this is the thermodynamic process. And look at this one. please carefully listen this part, this transparency, because it is the basis of thermodynamic systems. So here I have shown you that delta U, the change in the internal energy of a system, is given with Q, the heat added to the system, minus the work done by the system. Within this equation, you must be very careful with the signs, okay? This Q, the heat added to the system, and the work done by the system. So the heat and work can be negative or positive, okay? So depending on their signs, delta U changes a lot, okay? You must be very careful with the sign of Q and W. So here on the right side, we have a system with green color. This is the system. And here we have environment, surrounding environment, okay? And then we add this Q, heat, to this system, okay? Heat enters to this system, and this system does this W work. So just consider that here we have gas molecules, and then you heat this system, you give heat to this system, then let's say this gas molecules apply force on the surface of this system, then it expands, let's say, and then system does work. So remember the work is given with F times delta X, right? Or F times S. So this is the displacement. So the gas molecules applies force, and then the volume changes, okay? So look at the sign of the Q here on the left side. Q is positive because heat enters the system, okay? If heat enters to the system, then heat is positive. Look at the work here on the right side. Work is also positive. So here we have explanation for the first condition. The work done by the system produces an expansion, okay? Remember the work discussion in the previous lectures. Here we have, for example, ground, y is 0, and here there is a mass, and the height is equal to y, okay? Let's say y is y1, and then there is a weight, which is the force, okay? And then it moves like this. So direction of the force and direction of the displacement are in the same direction, okay? Then the work done here is positive, weight times delta y, displacement, okay? So same rules are valid here. So then you must be very careful with the sign of the work, okay? Here in this condition, I will go into detail, but I would like to discuss also here. So gas molecules within this system, let's say, applies force in this direction, and this system expands in this direction. Then the displacement and force are in the same direction. Then here we have positive work, okay? So look at the second condition here, this bottom figure. Again, we have a system, and we take heat from the system. So here, the heat leaves the system, then Q is negative. If heat leaves from the system, it is negative, okay? So just consider that here we have gas molecules within the system, and then we take heat from the gas molecules. Again, gas molecules apply a force in this direction, but what do you see here, that the size of the system decreases, okay? So displacement in opposite direction, then we have negative work done by the system. So system applies force on the surface of the container, let's say, okay? But displacement is in opposite direction, then we have negative work here. System does negative work. I will go into detail with this explanation. So in this part, you must be very careful with the sign of the Q and sign of the work. Now, let me discuss the work done during volume changes. Here, I have told you that you must be very careful with the sign of the Q, and you must also be very careful with the sign of the work, okay? Here, in this following transparencies, I will discuss the work done during volume changes. Just consider this piston here in the figure. Here we have a piston, and just consider that we move this piston to the right side. This is the motion of the piston. And then we have molecules, many molecules within this system, okay? And this molecule, let's say, choose this molecule. This molecule moves to the right, to the piston, and then it collides with the surface of the piston, okay? So it has this V velocity before the collision, and then after the collision, it bounces off piston, okay? So after the collision, the molecule goes back. So this is the final velocity of the molecule, okay? Molecule loses kinetic energy and does positive work on piston. So how I decided this positive work on piston? So look at the motion of the molecule at the beginning. It is moving to the right, and during the collision, it applies a force on piston, and the direction of the force is in this direction to the right, let's say positive X. And look at the motion of the piston. It is also along the positive X. Then the work is positive. The work done by this molecule on piston is positive. Okay, I hope this part is clear. Then let's discuss this second condition. Look at this one here. Again, we have the same piston here on the right side. And now we push the piston into the system. This is the motion of the piston. Piston is moving along the negative X direction. And here we have molecule. This molecule is moving along the positive X direction, and they collide here. Okay, so this is the initial velocity of the molecule before the collision. This is the final velocity of the molecule after the collision. So now, during this collision, this molecule here applies a force on the surface of the piston. This is the direction of the force along the positive X. Look at the displacement. Displacement of the piston is along the negative X, okay, because it is moving along the negative X direction. So since the force and displacement have different signs, opposite signs, then the work done by gas molecules is negative. Okay, and now just try to calculate the work done during volume changes. Again, here we have a system, a cylindrical container, and then let's say we have gas molecules within this system. System is gas molecules. Okay, then here we have a piston, and this is the surface of the piston. Okay, and piston moves to the right side along the positive x. Okay, this is the displacement of the piston, dx. And here we have force applied by the system. The system exerts this force on piston. Remember, the force here is written with pressure times area. This is the area of piston. This is the pressure applied by this system, gas molecules, and this is the force that system exerts on piston. Okay, so you already know this formula from your previous lectures. And what about the work? The infinitesimal work done by the system during the small expansion dx is given with this expression. The W is given with F times dx, force times displacement, and F is given with P times A, okay, pressure times area. Then we have this one. In addition to that, I can write this expression like this. Look at this expression. I can write this expression like this. The infinitesimal work done by the system is equal to P times, here I have A times dx. A is the area of the piston, and dx is the displacement, and then I can find this volume change dv. Okay, so instead of A dx, I can write this dv. This is the change in the volume of the system. Okay, so then just write this one here, dv. Okay, then I can write this one in this form. Okay, so this is the work done in a volume change. This is the initial volume of the system, V1. This is the final volume of the system, V2. This is the pressure, and this is the dV, the change in the volume. Do you have any question here? So what do you see here? Look at this work equation. Let me take this work equation here. Limit from initial volume, final volume, pressure, dV. Okay, this was the work. What do you see here? The PV gives us the work. During the last lecture, we have learned PV diagrams, right? Here we have volume axis. Volume changes from V1 to V2. And here we have pressure axis. Okay, so here we have PV diagram. And what do you see here, that on the left side within this equation, P times V, or the area under the PV curve, gives us the work, right? Look at this PV diagram. This is the initial position 1. This is the final position 2 in the PV diagram. At the beginning, the pressure of the system is P1 and the volume of the system is V1. And during this pass, what happens? During this pass, pressure decreases from P1 to P2, pressure decreases, and then volume increases from V1 to V2. Okay, remember last lecture, ideal gas equation, nRT. On the right side, let's say temperature is constant and amount of the gas within the system is constant, and here on the right side, let's say we have constant, And on the left side, PV is also constant. If you decrease the pressure, you have to increase the volume, okay? So you remember this discussion from the last lecture. And here we have an area under this curve. You see, we have an area. And this area is the work, okay? Volume goes from V1 to V2. And here we have P times dV. And the work is positive, okay? Work is positive here. Then what is this? This is expansion. Look at this piston. Let's say piston is staying here and this volume is V1, okay? And we have certain pressure P1 within the piston and we move the piston to the right. Now we have new position for the piston. Now piston is staying here. So what we have done, now we have new volume. And this new volume is given with V2, okay? And what about the pressure of the system? Now we have new pressure of the system, P2, okay? Volume is increased, but pressure is decreased. Pressure decreased and volume increased, and we have positive work, okay? This is expansion. You see, we have volume expansion here. This was the initial volume, smaller volume. Now we have V2. V2 is bigger than V1. Then we have expansion, okay? So during expansion, we have positive work, okay? And look at the compression. This is the initial position of the piston. So this is the initial volume of the system. This is the initial pressure of the system, okay? Then we apply, let's say, force in this direction and we compress this system, okay? Now let's consider that this is the new position of the piston and now we have new volume of the system, which is V2 and pressure is P2. Just consider that the system is ideal gas and this relation is valid. Okay, let's consider. Just consider that the temperature of the system is also constant. Okay, you can consider like this. So this side is constant. I have decreased the volume, then pressure will increase. Okay, you can expect this. And look at the PV diagram. This is the initial volume, V1, and this is the final volume, V2. This is the initial pressure, final pressure, and this is the initial condition of the piston, initial condition for the system. The volume is V1, and the pressure is P1, okay? And this is the final condition for the system. This is final volume, V2. This is the final pressure of the system, P2, okay? And system goes from 1 to 2, okay? Then the area here in the PV curve is the work. And what about the sign of the work? The sign of the work for the compression is negative. You can also imagine from this one. So here we have gas molecules, let's say, within this volume, within this system, and they apply force to the area of this piston, but the displacement of the piston is in this direction. So then we have negative work, okay? So during compression, the system does negative work, okay? During expansion, the system does positive work. So Now, let me discuss an expansion with constant pressure. Again, just consider we have a piston here. And this is the initial volume of the system. This is the initial pressure of the system. Okay? And in the second case, be careful here. We move this piston to the right, okay? And now we have much bigger volume compared to the first condition. The new volume is V2. But what about pressure? Pressure is constant, again P1. Okay? Pressure is constant. Just consider that you open a window here, and then let's say you adjust the pressure within the volume. Then we have constant pressures. So P1 and P2 are equal to each other. Okay, but V2 is bigger than V1. So look at the PV diagram here. This is the initial volume. This is the final volume. And this is the pressure. Pressure is constant. Pressure does not change. And the system goes from the initial condition to the final condition. So we only change the volume. Then we only have an expansion. Okay, volume increases. Then what about the work? Remember the work formula. V1 to V2 P dW, right? P is constant. I can take this P out of integral. Then I can write it like this, V1, V2, dW. And then if I solve this integral, then the work can be written like this, V2 minus V1. What about the sign of this work? The sign of this work is again positive because there is a pressure inside and gas molecules apply a force on the surface of the piston. Let me choose another pen. Here we have gas molecules, okay, and they apply force on the surface of the piston, okay, and the piston moves in positive direction. This is the change in the position of the piston, delta x. This is the direction of the force. Then again, we have positive work done by the system on piston. So this was the expansion with constant pressure. Now let me discuss three different paths on a PV diagram. So this is again PV diagram. This is the pressure axis. And here we have volume axis. And this is the initial position, initial condition, 1. And this is the final condition, 2. Okay. And from this initial to the final condition, I have three different paths. One path is this one. Second path is this one. From 1 to 4 and from 4 to the final condition. And the last possible path is this one, let's say, from 1 directly to the final condition. Okay, and I will investigate what is the work during this path and what is the work during this path and what is the work during this path. Okay, I will investigate the work done by the system. So look at the title, work depends on the path chosen. Okay, so depending on the path, the work will change and we will investigate this now. So then let's continue with the first pass. This is the initial condition 1, then we increase the volume. Look at this one. This is the pressure of the system. Pressure is P1, and this is the initial volume of the system. So during this pass from 1 to 3, the pressure is constant. Pressure does not change. But what happens to the volume? Volume changes from V1 to V2, okay? And here from 3 to 2, volume is fixed and pressure is decreased, you see? Let me clean the figure and use another color and repeat what I have explained here. This is the initial condition. We have P1 and volume 1, and we follow this pass from 1 to 3. During this pass, the pressure is constant. Look at the condition 3. The pressure is P1. And what about the volume? Volume here, it was V1, but here we have volume V2. Okay, volume is increased during this pass from 1 to 3. And now just continue to this final condition from 3 to 2. From 3 to 2, what happens? The volume is constant during this pass, but pressure is decreased. Now here we have P2, and P2 is smaller than P1, okay? And what about the work? We are dealing with the work, and the work is given with the area under this pass, okay? We have discussed in the previous transparencies, so the area under this curve gives us, the area under this pass gives us the work, which has been done by the system. And now let's use another pass to reach from condition 1 to the condition 2. So now I am following this pass. First of all, I keep the volume constant and then I decrease the pressure. Okay, we decrease the pressure. Pressure goes from P1 to the P2. Then from condition 4 to the final condition, pressure is constant, fixed, and then we increase the volume. Here, the volume was V1, and then volume is increased. Again, I traveled from condition 1 to condition 2, okay? But look at the area under this curve. The area is much smaller compared to this area here. So if you follow this path to reach to the final condition, you will have much less work. You have to do much less work compared to this path, which we have discussed here. Now, let me finish with the last pass. Again, we have PV diagram here. And I would like to travel from condition 1 to condition 2, okay? So here we have a curve from 1 to 2. So at the beginning, this is the P1 pressure. And what do you see? Pressure decreases. This is the final pressure, okay? And look at the volume. This is the initial volume V1, and this volume increases, okay? There is expansion, and also there is a decreasing pressure in the system. Then this is the area under this curve. This is the work done by the system. So then look at the title again. Work depends on the path chosen. Okay, now let's discuss the change in the internal energy of a system. This is the first law of thermodynamics. I have mentioned at the beginning of my lecture. It is given with this expression, delta U. The change in the internal energy of a thermodynamic system is given with Q minus work. Q is, be careful, heat added to the system, and W is work done by system. And you also must be very careful with the sign of Q and W. Heat can be positive or negative, and work can be positive or negative. Okay, you must be very careful during these calculations. So then this first law of thermodynamics is just a generalization of the conservation of energy. Okay, and both Q and work depend on the path chosen between states. I have discussed in the previous transparencies, the work depends on the path chosen. And in the previous lecture from thermal properties of matter, you remember that Q also depends on the path. Okay, but delta U is independent of the path. We will discuss this one. Okay, so this Q here within this equation depends on the path. Work depends on the path, but delta U is independent from the path. And if the change in the energy, in the internal energy, is very small, okay, if we have very small changes in the Q, if we have very small work, then we can write this infinitesimal change in the internal energy of a thermodynamic system like this. Then you can write the first law of thermodynamics like this. Do you have any question here? So related to this chapter, you should always keep this equation in your mind, and you should know what they mean. This is the heat added to the system, and this W is the work done by the system. I will give you some information, some application of this equation. Now let me continue. Just consider that the internal energy of a system increases. Okay, just consider this condition. Here we have a system in the figure. Let me choose another pen with another color. This is the system. And just consider that within this system we have gas molecules, and we give heat to this system. Okay, we give heat and we give this energy to the system. It is given with 150 joule. And then just consider that this system expands and then does this work given with 100 joule. And what about the change in the internal energy of the system? So we gave this energy to the system, but we spent this energy. Okay, you gave this energy, but you spent this energy. And what about the change in the internal energy of the system? This change is given with this expression, the energy taken and the energy spent. Okay, heat added to the system and the work done by the system. Just put here positive 150 joule, just put here 100 joule, then the result is positive 50 joule. Then internal energy of the system is increased. Now we have positive change in the internal energy of the system. Okay, do you have any question here? And just consider the condition with the internal energy of a system decreases. Look at this figure again. Now Q is negative. What is the meaning of this negative sign here in the Q? We take heat from the system, okay? In the previous case, we add heat to the system, but now we take heat from the system. We take energy from the system. And then there is a shrinking or compression, okay? So then we have negative work. There's a compression here, negative work. What about the change in the internal energy of the system? It is given with delta U. It is equal to Q minus W. Now Q is negative, minus 150 joule. And what about the work? Work is also negative because we are talking about compression or shrinking, okay? Then here we have negative 100 joule. This will be positive, but here we have negative sign. Then the result is negative 50 joule. Okay, this is the change in the internal energy of the system. Internal energy of this system is decreased, okay? Do you have any question here? Then let me discuss this condition. The internal energy of the system remains the same. Look at the figure again here. We have a system and we give energy to the system. This is the heat added to the system, and the system expands and then does positive work. So this is the heat given to the system. It is equal to 150 joule, and this is the work done by the system, 150 joule. So we have given this energy to the system, and system spends this energy, okay? Then just put the numbers here within this equation. Q is 150 joule, the sign is positive, and here we have positive work, 150 joule, and the result is 0, okay? There is no change in the internal energy. Okay, so here we have very nice example related to the first law of thermodynamics. So look at this equation, Q minus work. Our body, human body, is a thermodynamic system, and when this lady does a push-up, her body does work, okay? So she spends energy, okay? She spends energy and does positive work, okay? And during this exercise, this body warms up, okay? So temperature of the body increases during the exercise, and by perspiration and other means, the body rids itself of this heat. So this heat transferred to the surrounding, to the environment, okay? So from body to the surrounding, there is a heat transfer. Then this Q is negative, okay? Heat does not enter into the body. The heat leaves from the body, then it is negative. At the beginning of my lecture, I have told you that you must be very careful with the sign of the Q. Then we have negative Q and positive work. Just write the change in the internal energy. Here we have negative Q, negative sign, and here we have positive work. Then the result is negative. Okay, so what do you see here? By doing exercise, she loses energy, okay? Internal energy of this lady decreases, okay? She loses energy. So what about the energy within this body? Some part of the energy is stored in our body in the form of fat, okay? And then you spend energy, then it means that you lose weight. You spend some part of the fat within your body, okay? You lose energy, your internal energy decreases during exercise. It means that you spend some part of the internal energy stored in your body in the form of fat. Do you have any question with this example? This is very nice example related to the first law of thermodynamics. If something is not clear, please let me know. Okay, here another example related to the past. What I have told you that the heat depends on the past and work depends on the past, okay? But delta U, the change in the internal energy of the system, does not depend on the past, okay? Here we have a cup of coffee, okay? So just consider that at the beginning, this cup is empty, and then it has certain temperature, and you add some coffee. This coffee has certain temperature, and you add some milk, let's say, and this milk has certain temperature, okay? And you add some hot water, and this also has some certain temperature, okay? Then finally here we have a coffee, okay? So we added heat to the system, but what about the final internal energy of the system? Now let me continue. Look at this sentence here. The internal energy of a cup of coffee depends on just its thermodynamic state. So this cup has certain temperature. We have a temperature of environment, and then we have temperature of water. We have temperature of coffee, okay? So the internal energy just depends on the thermodynamic state. How much water you added, it is important because you add hot water, and how much ground coffee you added. So this thermodynamic state depends on this. Internal energy of the thermodynamic state depends on these parameters, and then it also depends their temperatures, okay? So just consider that you added 10 milliliter of water with the temperature of 90 degrees Celsius, and you added, let's say, just numbers, okay, 2 grams of coffee with the temperature of 25 degrees Celsius, okay? So you added these things, and then this cup has certain mass, okay, and temperature, let's say 22 degrees Celsius. And then the final temperature or the internal energy of this complete system depends on the amount of water, amount of ground coffee, and also depends on their temperatures. I think this is clear, but look at this important sentence here. It does not depend on the history of how the coffee was prepared, that is the thermodynamic past that led to its current state. So you can prepare this coffee with this method. You add the water, first of all, and then you add the coffee. Okay, or you can also prepare this coffee like this. You add the coffee first, and then you add the water. Okay, so the internal energy does not depend on this pass, okay? internal energy only depends on the amount of coffee and amount of water and their temperatures. I hope it is clear. Then let me discuss the cyclic thermodynamic process for a human day. Here there is a sleep, and during this sleep we spend energy, we do work, okay? You take breaths and you give the breath and you move during sleeping, okay? So your body is working, your system works, okay? So you spend energy, so you do positive work during sleeping, okay? Then you spend energy, you can consider like this. And then you wake up and you have breakfast, 1 hour, okay? So during this breakfast, you get energy. You take energy into your system, and during this eating, you spend energy, you do work, okay? Your arms, your hands are working, your body is working, okay? So you spend energy, and then after breakfast to the lunch, you do work, okay? Let's say you study 4 hours, and then you do work, you spend energy, okay? And then during lunch, again, you take energy into your system, Q is positive, and you spend this energy during eating lunch. Look at the energy spent during breakfast and lunch. Just consider you spend same energy, you do the same work, and you take the same energy during the lunch and during the breakfast. Okay, look at the numbers. Then after lunch to the dinner, you work again. This is the afternoon work, 4 hours, and you spend energy during this working, okay? So this is the work, positive, and we have 1 hour dinner, and then we take energy into our body. This is the positive Q. We add heat to the system, and then during this dinner, we spend energy. This is the work done by the body. So look at this work done by the body during dinner, during lunch, during breakfast. So you take energy into your body, but also during eating you do work, okay? Then you spend energy. And then after dinner, you do exercise 1 hour, and then you spend energy, you do work, okay? Just compare with the work during the eating. So during exercise, you spend more energy, okay? Then after exercise, you study, you watch TV 4 hours, let's say, until sleeping, and then you do work, you spend energy. So here we have different colors. Be careful, it is very simple and very nice example. So during breakfast, during lunch, during dinner, you add heat to the system, you add energy to your body, okay? But during these works, we spend energy, we do work, okay? We do positive work. And then what about the change in the internal energy of the body? It is given with Q minus work. We have positive Q due to the breakfast, due to the lunch, due to the dinner, and put them here. And we have many works, positive works, put them here. So if they are equal to each other in total, then the internal energy of the body will be 0. There will be no change in the internal energy, and then your body will be fit, okay? Now let me discuss the 4 kinds of thermodynamic processes. Actually, you have learned all of them, but now I will go into detail. The first one is adiabatic process. The second one is isochoric process, isobaric process, isothermal process. So what I mean with the adiabatic process. In adiabatic process, no heat is transferred into or out of the system. So Q is 0. Here we have a system. Okay, just consider we have molecules, gas molecules, particles within this system, and there is no heat transfer, no heat taken from the system, no heat added to the system. So Q is 0 in adiabatic process. And what about the internal energy of the system? The internal energy of the system is given with Q minus work, right? If the Q is 0, then internal energy, the change in the internal energy can be written with this expression. In adiabatic process, we have this one, okay? There is no heat transfer into the system or out of the system. And what about the isochoric process? In isochoric process, we have discussed this one during the last lecture. The volume remains constant. Volume does not change. V is constant. Isochoric process. What I mean? Just consider a piston here. And we have gas molecules within this piston, and it has certain volume. And this volume is constant. What is the meaning of this? This piston does not move to the right, or this piston does not move to the left, okay? The position of the piston is fixed. Then what about delta X? 0. There is no displacement, okay? Because volume is constant. If delta X is constant, if delta X is fixed, it is if delta X is 0, if displacement is 0, then what about work? Work is also 0. So in isochoric process, the volume remains constant, then the work is 0. Volume constant, work done by the system is 0. What about the isobaric process? In isobaric process, pressure remains constant. We have constant pressure. We have discussed this one. In case of constant pressure, work is given with this expression. When the pressure is constant, then the work done by the system is given with this expression. We have already discussed this condition. Then this is the isobaric process. In isobaric process, the pressure remains constant. And the last one, isothermal process. In the isothermal process, the temperature remains constant. Okay, temperature remains constant. The initial temperature and final temperature are equal to each other, you can say. Okay, so from the names, you can understand isothermal, it is related to the temperature. Isobaric, so it is related to the pressure. Isobaric means the same pressure. Isochoric, it is related to the volume. And adiabatic, in case of adiabatic, there is no heat transfer. Okay, heat transfer is 0. So we have 4 kinds of thermodynamic processes, and in the following transparencies, I will give you few examples. Here we have an example for the adiabatic process. Here you see a cold beverage, okay? There is a beverage here, okay? Just consider soda or other beverages. And then there is a lid of this beverage. This is the lid of the bottle, let's say, okay? And then you open this lid, and there is a pressurized gas inside the bottle. So let's consider that this is the bottle, and this bottle has certain volume and certain pressure, okay? And when you open this lid of the bottle, this pressure will go out, okay? So gas molecules will go out. So there is a high pressure within the bottle, you open the lid, and then gas molecules within the bottle will go out. So the pressurized gases inside the bottle expand rapidly and do positive work on the outside air. So here you see gas molecules, okay? This is actually very easy to understand. I hope I can explain it. So this was the initial condition. The lid is closed, and then we have opened the lid. This is the final condition. Now lid is opened. And here we have gas molecules. Okay, at the beginning, gas molecules are compressed here with high pressure, and now some part of the gas molecules are released. Okay, so then this gas molecules apply force on the outside air. Okay, they apply force on outside air, then they do positive work. They apply force and they produce displacement of the air molecules, air particles, okay? Then they do positive work. There is little time for the gases to exchange heat with their surroundings. So this gas molecules within the bottle has certain temperature, T1, let's say, and here we have surrounding molecules in the air has temperature of T air, let's say, and the time is limited, very short time, then they don't have any heat exchange. Just consider like this, there is no heat exchange, and then Q is 0. There is no heat exchange between the gas molecules of the bottle and the gas molecules of air. There is no heat exchange, then Q is 0. Then the process is adiabatic, okay? And what about delta U? Internal energy, Q minus work done by the gas molecules. Q is 0 and work is positive. Then here we have the internal energy of the expanding gas. What do you see here? We have positive work, right? This is positive. But in front of this work, we have negative sign. Then what about the delta U? The internal energy of this gas molecules will decrease. Here we have gas molecules. They were within the bottle at the beginning. Now they are here, okay? And the internal energy of this gas molecules will decrease. Then this makes water vapor condense and form a miniature cloud. So they lose energy, okay? Then this makes water vapor condense, okay? And then you see this type of behavior here, like a cloud, okay? When you open the lid of the beverage. So this is due to the adiabatic process. I hope it is clear. If it is not clear, please let me know. Then let me continue with the isobaric process. What was the isobaric process? Pressure is constant in isobaric process. Okay? Pressure is constant. And now let's have a look. Delta U. So that's because the air pressure above a saucepan or frying pan or inside a microwave oven remains essentially constant while the food is being heated due to the isobaric process. So here we have a thermodynamic system, and let's say we have water or food within this saucepan or within a frying pan. Okay, and you transfer heat to this system, okay, but there is no lid here. Then the pressure will not increase, pressure will be constant. If you put a lid on top of the pan, okay, and if you tightly close this lid, then the pressure will increase. When you add heat to the system, the pressure will increase. But here there is no lid and pressure will not increase. Okay, this is the isobaric process. P is constant. And now let's discuss all these thermodynamic processes in a single graph. So what kind of processes we have? We have adiabatic process. We have isochoric process. We have isobaric process. We have isothermal process. Okay, we have 4 processes, and in this case, heat transfer is 0. In this case, volume is constant, and in this case, pressure is constant, and in this case, temperature is constant. So now here we have a PV diagram. Okay, this is the pressure axis, and this is the volume. Now let's discuss the adiabatic process. Here we have adiabatic process. What was the adiabatic process? In adiabatic process, the Q is 0, then the change in the internal energy is given with negative work. Work is positive, but here we have a negative sign. Then we expect a decrease in the internal energy in adiabatic process. Okay, so this is the starting position, this A here. Let me choose another color. Here we have A point, okay, and here pressure is PA, and the volume of the system is VA, okay. Then I follow this path. I come to this condition 1, okay, following this path. So what happens here? Look at this curve here. The temperature of this curve is TA or T4. We have done it during the last lecture. And here we have temperature of this curve. This is equal to T1. This is the temperature of this curve. And in adiabatic process, what happens? Look at the pressure. Pressure decreases and volume increases. You see, this is the initial volume and this is the final volume. Let's say V1 here. Okay, pressure. This is the initial pressure PA and this is the final pressure P1. So the system expands, okay, and during the expansion we have positive work and here we have negative sign. Then we have a decrease in the internal energy of the system. In an adiabatic process we have decrease in the internal energy of the system. Then what do you see here? This T1 is smaller than the TA. So this was the adiabatic process. Now let me continue with the isochoric process. In isochoric process, volume is constant. Volume does not change. Look at this condition. This is the starting condition A. The pressure is PA and the volume is VA. And we have this path from A to 2. Okay, what do you see here? Volume does not change. This is isochoric process, but the pressure decreases. Okay, so what do you see here? The temperature of this curve we have done during the last lecture is TA or T4. And look at the temperature of this curve. temperature of this curve is T2, and T2 is smaller than TA. How I know this one? From this ideal gas equation. Okay, if you increase the temperature, this will increase. If you decrease the temperature, then this will decrease. We have discussed all these things during the last lecture. And now let's continue with the isobaric process. P is constant, pressure is constant. Here we have the position or condition A, and pressure is PA, and volume is VA, and we travel along this path. Now this is the final condition. What do you see here? Pressure does not change. P is constant. It is isobaric process, and this is the final temperature, which is given with T3, and this is the initial temperature of the system, TA or T4. Why I'm writing this one? Because here we have fourth point and they are on the same PV curve. So during this path from A to 3, we have constant pressure, then the process is isobaric. And the last one, isothermal process. T is constant. Here we have the initial condition for the system. Pressure is PA and the volume is VA. And here we have this path from A to 4. Volume here is given with V4 and the pressure is given with P4. Okay. So what about the temperature? Since these two conditions are on the same PV curve, then what about the temperature? Temperature of the A condition and temperature of the fourth condition are equal to each other. Then temperature is constant. This is isothermal process. Do you have any question here? Let me continue with the internal energy of an ideal gas. Here we have an insulated system, and these are the insulations. Okay. And there is no heat transfer into the system and out of the system. And here we have a breakable partition. And here we have gas and gas molecules at temperature T and volume V1, okay? And the pressure is P1. And just break this breakable partition, then this gas will go here. Now we have another volume. This is the second condition. Now volume is V2 and it is bigger than V1. And what about the pressure? If the system is isolated, now we have pressure 2, but this pressure 2 is lower than P1, right? How I know this one? Just write this ideal gas equation. So the temperature of the system is same because it is insulated and this part is constant. And if I increase the volume, then pressure will decrease. So then look at this statement here. The internal energy of an ideal gas depends only its temperature, not on its pressure or volume. Okay, so delta U depends on the temperature. We will give some examples. The temperature of an ideal gas does not change during a free expansion. Here, the gas expands, but the temperature does not change because the system is isolated, okay? So the gas expands, volume increases, but then pressure decreases. Okay, now let me discuss the heat capacities of an ideal gas. This is the CV is the molar heat capacity at constant volume. We have discussed during the last lecture, but here you must be careful. This CV is given for the constant volume. Volume is constant. And now let's consider here we have a container with fixed volume. Okay, volume is fixed, volume does not change, and we add heat to this system. Okay, then at the beginning, the initial temperature of the system was T, and after adding this dq heat, this is the final temperature of the system. So final temperature of the system is increased. And the relation between heat and temperature increase is given with this expression. We have added this heat and we have increased temperature with dT. And this expression is given with N times CV times dT. To measure CV, we raise the temperature of an ideal gas in a rigid container with constant volume, ignoring its thermal expansion. So since we considered that the container has a fixed volume and it does not expand, okay, then we have constant volume, okay, the initial volume and final volume are same, then we have N moles of ideal gas within the container, and we add heat, which is given with dq, and due to this dq, the temperature of the system increases. And here we have another heat capacity of an ideal gas, but in this case at constant pressure. In the previous case at constant volume, here we have molar heat capacity at constant pressure, and we show it with Cp, C subscript P. So to measure Cp, we let the gas expand just enough to keep the pressure constant. So we have to keep the pressure constant, and we will increase the temperature of the system. Look at this one. Here we have a volume container, and just consider here we have a movable piston, okay? And then here we have N moles of ideal gas within the container, and we add heat to the system. If we add heat to the system, then the temperature of the system will increase, okay? This is the initial temperature of the system. This is the final temperature of the system. So this temperature of the system is increased with dT. And this increase happens due to the adding heat to the system at constant pressure. And this heat is given with this expression, Ncp dt. So how to keep the pressure constant? So if you add heat to the system, and if the volume is fixed, then pressure will increase. But if you increase the volume, if you move the piston to the up, then you will increase the volume. Then you can keep the pressure constant. Okay. You can adjust this one in this way. And now let me continue with the relating Cp and Cv for an ideal gas. Okay, so what is the relation in between? To produce the same temperature change, more heat is required at constant pressure than at constant volume, since delta U is the same in both cases. So I will explain what I mean. Just consider that here we have an ideal gas, and I would like to increase its temperature with delta T or dT, and I am adding a dq heat. So if the volume is constant, then we have learned that this dq is given with an molar heat capacity for constant volume and dT. Okay, and if the pressure is constant, dq is given with n Cp dt. Okay, so look at this statement. To produce the same temperature change, dt, more heat is required at constant pressure than at constant volume. In constant pressure, you need more heat because molar heat capacity for constant pressure is bigger than the molar heat capacity for constant volume. Okay, this expression here. You would like to produce the same temperature change, dt, and then you have to add heat to the system, okay, in order to produce this dt. So just take this dt from this expression. Dt is given with dq over n cv, and just take this dt dq over n Cp. Okay, Cp is bigger than Cv. Then, in order to have same temperature change, then you have to add more heat in case of constant pressure. I hope this is clear. So here we have Cp. What I have told you that the molar heat capacity for constant pressure is bigger than the molar heat capacity for constant volume, and we have this relation. Cp is equal to Cv plus R, and this R is the gas constant we have already discussed during the last lecture, and it is equal to 8.314 joule per mole per Kelvin. Okay, and this is the pressure versus volume graph, PV graph, and here we have two curves. This is the initial temperature of the system, initial energy of the system, and then just consider like this. Here we have a volume. It has certain temperature T1 and certain energy U1, and we add heat to the system, and now it has temperature T2 and it has energy U2. Okay, when you increase the temperature, this PV curve will be like this. So here the temperature is T1, here temperature is T2. Okay, so you can produce this condition in two ways: volume constant or pressure constant. So let's consider that this is the initial condition. Pressure is P1, volume is V1. And then just consider that volume is constant and I am increasing the pressure. Volume is constant and I add dq heat to the system, pressure increases, but volume is constant. We have discussed this one in the previous transparency. And what about the work? Work is 0 because volume is constant. Okay, then delta U is only given with the Q because we have given heat to the system. Okay, and it increases the internal energy of the system. Okay, and look at the constant pressure process, the second case. This was the initial pressure and this is the initial volume, and here we keep the pressure constant. Okay, we add heat to the system. Okay, and volume increases, but pressure is constant. In case of constant pressure, what about the work? Work is positive. Okay, work is positive, and delta U is given with Q added to the system and this one, and here work is positive. And if you put this one to this side, then you can write the heat added to the system is given with this expression. Okay, where we have it. So this is the graph for heat added to the system to produce the same temperature change by keeping the volume constant and by keeping the pressure constant. So this is the ratio of heat capacities. Here we have molar heat capacity for constant pressure, and this is the molar heat capacity at constant volume, and this is the ratio of heat capacities shown with gamma symbol. And for monatomic ideal gases, it is given with 1.67. What I mean, for example, argon, okay, or helium. So these are the monatomic gases. And for diatomic ideal gases, it is given with 1.4. What I mean, hydrogen gas, oxygen gas, or nitrogen gas. Okay, these are the diatomic gases. And now let me finish with this transparency. Adiabatic processes for an ideal gas. In an adiabatic process, no heat is transferred in or out of the gas. I have already discussed Q is 0, and then delta U is given with minus work. Okay, and here we have PV curve for an adiabatic expansion. Why we call it expansion? Because what do you see here? Volume increases. This is the initial point, and this is the final point. And during the adiabatic process, we have this type of path. Okay, what do you see here? Pressure decreases, but volume increases. And then this is expansion. And we have learned that during the expansion, we have positive work. Okay, and then just write the change in the internal energy of the system, Q minus work. Q is 0 and work is positive, then delta U is equal to negative work here, and the internal energy of the system decreases, okay, and its temperature drops. Look at this one. This is the TA, initial temperature of the system, and this is the TB, final temperature of the system. And what we see here, that TB, final temperature, is smaller than the initial temperature of the system because internal energy of the system is decreased in an adiabatic process. I hope it is clear. With this one, I have finished this lecture. Take care of yourself. Bye-bye.